Welcome everyone to the CFA Colloquium. Today, we are fortunate to have Professor Reva Williams from University of Toledo to come and talk to us about energy extraction from black holes. So Reva got her bachelor's degree at Northwestern, master's and PhD from Indiana University. Then she held positions at University of Florida, Bennett College, and I think one or two other places. But right now she's a professor in the University of Toledo, Ohio. Now, I knew that I had met Reva at some point because I could even picture her in my mind, but I couldn't remember when and where. She told me we met at some Marcel Grossman conference some years ago. And for those who don't know, the Marcel Grossman is this kind of preeminent event in general relativity and relativistic astrophysics. It happens every few years in different parts of the world. So that is where we met. And this is something I definitely didn't remember. Reva reminded me that she and I were also on a proposal to do some measurements of radio jets in microquasars. This was a proposal submitted by Bob Gelming, unfortunately, just before he died. So I don't even know if the observations were carried out. But yeah, so we have some links. So it's very nice. So it's wonderful to see her here again. And I should just say that, the specialty of what Reva is doing is energy extraction from black holes, but she's going to the foundation. She's looking at Penrose process as Penrose originally described it in terms of particles. Many of us study energy extraction through magnetic fields, and it's called Blandford's-Nayak, Blandford-Payne, and that's a nice mechanism. But Reva thinks, and I think she's the first to actually pursue this in detail, that we can do this directly with particles. And I think that's what she's going to talk to us about today. The title is up there on the screen: Extracting X-rays, Gamma rays, and Relativistic E plus E minus pairs from the ergosphere of rotating black holes using the Penrose mechanism. Okay, Reva.
Good afternoon. Today, you all are going to learn about black holes and their energy extraction mechanism. Now, many of you, I'm sure, recognize these scientists. They are Isaac Newton and Albert Einstein. Not only did these scientists, with their laws and theories of gravity, lead us to the knowledge of black holes, and particularly Einstein, but on a more personal level, these scientists are the reason I'm here today giving this talk. That is, early on in my quest to find out which area of science I wanted to pursue as a career, when I was first introduced to these scientists' laws and theories of gravity and motion, I fell in love with the physics. And that basically sealed my faith in my becoming an astrophysicist, one that studies the physics of the universe. So let's get started. So my agenda, first I will give an overview of what black holes are. Next, I would talk about the rotating black holes, the Penrose energy momentum extraction, and observations and model correlations. And then I will conclude and take questions. These are my references. I'll give them again at the end of the talk, but the material is coming from my Physical Review Journal paper, 1995, and my Astrophysical Journal paper, and then a paper that it didn't get published, but it has a lot of material in it. I plan to submit it again, update it and submit it again. Now, I want to acknowledge, Henry he was my dissertation, I'm not my dissertation advisor, but my postdoctoral advisor, and unfortunately he passed away. And I want to acknowledge Fernando de Felice, I think I'm saying that right, because he was the one that actually let me know what my particles were doing, because while I was pondering with the angular momentum, with the space coordinates momenta, and the advisor and I knew that they had this large angular momenta, and also they had a moderate polar coordinate momenta and a sort of a small radial component when you compare them. But I knew they were coming out in the form of jets, but I hadn't worked it out in detail because I had planned to do a time evolution. So I hadn't really worked it out to see just what the particle orbits were doing. And then at the Marxer-Grossman meeting, I was given a talk, and Fernando, he was there. And after I finished, he directed me to a paper that he had just published in the Astrophysical Journal, and it was talking about these vortical orbits. And so he had predicted basically the particles, what I have gotten out from my model. He predicted them by just studying the geometrics of the curved black hole. And then, of course, I thank Roger Penrose, because all along I would go to conferences and he was encouraging me, so I had to acknowledge him. So what are black holes? Black holes were predicted to exist from Einstein's theory of general relativity in 1916. In short, they describe motion in a gravitational field. They show that clocks run slower in a gravitational field. And it also shows that space-time is curved around a massive body. And usually we use this analogy of a rubber sheet. And so the mass is here, and then these are trapped orbits. Black holes are one of the most fascinating objects in our universe. They are a storehouse of a tremendous amount of energy. It wasn't until the 1990s that we began to understand the physics of black holes. And I like to think that my work did have a lot to do with it. And, you know, I heard that from panel reviews that my work contributed significantly to our understanding. They were observations in 1994 by the Hubble telescope strongly suggested that black holes indeed exist in nature. Because when I first started studying black holes, it had not been confirmed or strongly suggested that they exist in nature. So we were basically still looking for them. And I even had some people ask, well, what if they don't exist? After I was way into my dissertation. So, and then in 2001, it was strongly suggested with direct evidence of energy extraction being extracted from rotating black holes. So I was really happy about that. Black hole masses can range from greater than 3 times our sun's mass up to 1 billion times our sun mass. Black holes are believed to be the most energetic objects in our universe, and they power such objects like quasars and gamma ray bursts, objects that we believe to be powered by black holes. So I want to say something a little about quasars and gamma ray bursts. Quasars were discovered in 1963. They are the most distant objects in the universe, and their energy output is about 100 times, from 100 to 1,000 times the luminosity of our galaxy. Yet they are no bigger than our solar system, so that makes them really mysterious. They are associated with bipolar jets emanating from their cores, and we observe very high energy particles such as electrons, positrons, gamma rays, and perhaps protons, but I didn't cover protons in my calculation because it was believed that they wouldn't really, by them being so heavy, they wouldn't really contribute to the particles in the jet. And we know from synchrotron radiation that magnetic fields are present, and also the spectra are non-thermal. So we suspect that Compton scattering or inverse Compton scattering is there. So in addition to them having a storehouse of energy, black holes can also have rotational energy and electromagnetic energy. So that's why some people are working from the electrodynamical point of view, like the Blanchet-Denied models. And then black holes have no hair. So they call it the no hair theorem, and that's because we do not know the progenitors of a black hole. Like, for example, the supermassive black hole. We don't know if there were, say, a large group of stars that supernova and turn into black holes, or was it a supermassive star that turned into a black hole? We don't know. The only thing we know is the black hole's mass, the angular momentum, and the electrical charge. So that's why we say that they fall under the theorem of no hair. So this is a picture of a galaxy, and here is showing the core. So the geometry around it suggests that there's a black hole. This is an artist's conception of an active galactic nuclei. And so these jets are what I am attempting to explain, as well as the core energy. Then this is Quasar 3C 175. And here, this is in the radio, and you can see the jets emanating from the core. And these jets extends out to kiloparsecs. So it must be something really powerful going on in order to produce such jets. This is the X-ray of Centaurus A. And here you can see the jet. Now I want to say something about gamma ray bursts. Gamma ray bursts, they were discovered in the 1970s. They appear to be the most energetic events in our universe. And at one time, we didn't know, we were wondering, like, how could something have so much energy? But then later we found that the jets are emitted, the energy is emitted in the form of jets. So if the jet is pointed towards us, then it's going to look like it has a tremendous amount of energy. But they do have a tremendous amount. But sometimes, we didn't understand that they were jets. And so, for a object to be radiating that much energy all, from the whole surface, that would be quite unusual. Gamma ray bursts, we know that they are formed from the birth of a black hole. It could be a supernova explosion prior to the formation of a black hole, or two neutron stars that exceed the mass, of course, of a neutron star, and they qualify to be a black hole. So when two neutron stars collide, then they would turn into a black hole. So that's a newly forming black hole. Or it could be a neutron star being swallowed by a black hole. So they all have to do with the black hole. Now, I want to say something about astrophysical black holes. Now, quasars, we know they were discovered in 1963. Then in 1991, we found that galactic stars or black holes, they produce the similar radiation as the quasars. And so I had found that the calculations are scale independent, because I would get the same energy out from a solar-sized black hole as I would get out from a quasar. The only difference is that the accretion disk makes a difference, or the accretion rate. So quasars, they are important. Quasars, they have masses from 10 to the 6 to 10 to the 9 solar masses. And microquasars that could be found in our galaxy, they have masses from 7 to 20 solar masses. They're important because they have variabilities. Their jets can expand and decay over a period of a month. So if we study the microquasars, then it lets us know what could be happening in quasars on a larger scale. The luminosities are different. The variability timescales for quasars are from an hour to 2 years. And then for the variability in the X-ray for a microquasar, it's milliseconds. So it's important to study the microquasars. The jet lengths are for quasars on the order of kiloparsecs, and for microquasars less than a parsec. The energies for quasars range from radio to hard X-ray or gamma rays up to GeV and then TeV if the jet is pointed towards us, as in the case of blazars. And so for the microquasars, it's from radio to soft X-ray, gamma rays, up to 10 to 20 MeV. And so again, that depends on the accretion distance. So now I want to say something about rotating black holes, Penrose energy momentum extraction and observations and model correlations. So the physics of a rotating black hole was worked out using Einstein's general theory of relativity by Roy Kerr in 1963. So this diagram, it shows some of the properties of rotating black holes. And so if you say start out toward the event horizon, you'll run into a region called the stationary limit. And inside this region is the ergosphere. Once an object is in this region, it must rotate in the direction that the black hole is rotating. And so this is because of the frame drag and the angular momentum of the black hole producing the frame drag. For a Kerr black hole, so here's the event horizon. This is the event horizon, even though light cannot escape, it's not the true horizon. It's not the true, singularity. The true singularity for a rotating Kerr black hole is a ring. And it's confined to the equatorial plane. And inside the ergosphere, you have particle orbits. Now these particles that orbit inside here, they are at the point of the closest approach. That's not the word I want to say, but I can't think of what I'm trying to say. Okay, so let me move. Now this is the Kerr black hole. I just brought this in so that you can see the metric. This metric, it defines the separation between space and time, space-time events. So it's sort of like a distance formula, everybody's familiar with that. So it defines the distance between an event, a space-time event. And then these are just the parameters here, or the factors. Let's see. The A is the angular momentum per unit mass parameter. And so this governs the rate of the spin. M is the mass of the black hole. Omega is the frame dragging velocity. And then these parameters. The black hole has important properties to occur rotating black hole. So before reaching the event horizon, again, I just said that you encounter the ergosphere. Now, even though we always measure positive energy, the infalling particle inside the ergosphere can have either negative or positive energy. And this is significant in extracting energy from the ergosphere. The negative energy particles, they can never leave the ergosphere, but the positive energy particles can. And they can escape from the strong gravitational pull of the rotating black hole. Now, since nothing can escape from the event horizon, the identification of a black hole is its gravitational influence on nearby matter. There are two popular theoretical models that have been proposed to extract energy from a rotating black hole: the Penrose mechanism and the Blanchard model. I'll concentrate more on the Penrose mechanism, but I will mention some properties of the Blanford type models. So in 1969, Roger Penrose, he proposed a way to extract particle energy from the ergosphere. And we now call this the Penrose mechanism. So this is the idea behind the Penrose mechanism. You have a particle inside the ergosphere, and it decays into two particles. One of the particles becomes trapped, and it has an energy less than 0. The other particle escapes with the positive energy. So these, we'll call these E1, E2, and E3. So from the conservation of energy, E1 is equal to E2 plus E3. Now, if you solve for E3, then you just get the regular difference between the energy of the E1 and E2. But if E2 has an energy less than 0, then E3 is going to equal to E1 plus the absolute value of E2. And so that means that energy is extracted because this is more energy than the particle, the initial particle had. Now, there are problems with the classical Penrose process. Number one, in order for the particle to have any kind of energy or to be able to extract energy, then the breakup has to be at the speed of light. So if you have a star is not going to break up at the speed of light. So, and also, okay, before I say the solution to that, then also the efficiency we measured was very low. So to overcome this problem, Piron and I think Kotz, they proposed that the particles should be, that it should be a relativistic scattering. And then that way the particles would break up at relativistic speeds. And so this is what led me to investigate the inverse Compton scattering and the pair production. Now, Piron and Shaham, they had performed the Penrose Compton scattering. That's when I say inverse Compton scattering, sometimes I refer to it as the Penrose Compton scattering. They looked at they did the geometry and they were able to extract some energy out, but very little, like on the order of 1 MeV. And the reason for this was that when they applied the escape conditions, they knew the escape conditions along the equatorial plane, but in order to, so they knew the escape condition, and so they assumed that the particle escaping above and below the plane would have the same, it would be all right to apply the equatorially confined escape conditions. And so therefore, they didn't get a lot of energy out. So for a long time, people thought the Penrose mechanism really didn't work. Now, my model consists of a supermassive black hole, and particles from an accretion disk are assumed. And I'm assuming that it's a thin disk ion corona, or it's also called a two-temperature bistable disk. And the two temperatures because of the difference in the electron temperature and the proton temperature. And I'll talk more about that because I had to duplicate, I duplicated the accretion disk models in order to be accurate in the particles that I would use in the scattering process. So the Penrose mechanism is used to extract energy momentum by scattering processes in the ergosphere. Now, these radii are important. R0 is the static limit that I talked about. R sub ms, this is the radius of the marginally stable orbit. This is the last stable orbit for the accretion disk. In this region is where I'm performing the Penrose Compton scattering. This radius is the marginally bound orbit. This is the last orbit for material particles. And then you have the photon orbit. where light is trapped encircles the black hole. And so the observations from the event telescope, well, it's basically we're looking at the shadow, but that light is from the photon orbit. And then here the event horizon. So the scattering processes I performed was the Penrose Compton scattering. And we know that an electron is in orbit. This is a target electron. It's in orbit inside the this region. And a gamma ray comes in, or just a photon from the accretion disk, a low energy photon, and it scatters. The electron is put on a negative energy orbit, or a orbit that's or lower energy orbit. So in my case, in my paper, I called some of the scattering processes, I say quasi-Penrose, because not all the particles are put on negative energy orbits. Here I did the gamma P, no, right here. Okay, the gamma P scattering, in which the gamma ray, or in this case it is a gamma ray, and it pair produced inside the Coulomb field, or outside the Coulomb field of the proton. This one was not very fruitful. It had been predicted that you should get energies up to GeV, or comparable to the rest mass energy of the proton. But in the cross section, when it was derived, it had in it that the proton did not recoil. So when I did the scattering process, I only got out the energy that I had put in. And I think that was because of the limit that was imposed when deriving the cross section. This Penrose pair production was very fruitful. This is done at the photon orbit. And so you have a target photon of very high energy, and then you have a photon from the accretion disk, and they pair produce into relativistic electron-positron pairs. And so the model can predict the spectral ranges of particles intrinsic to, and I say, quote, black hole radiation by the Penrose method. That should go faster. Okay, here I'm just showing this schematic diagram of the model that I investigated. So here again, the ergosphere, and of course, this is not drawn to scale. The accretion disk, this is like, we used to call this what, the alpha accretion disk. This is the optical thick accretion disk. And now Lightman, this was, I guess it was like 76 or 1976 or something. He took and looked at the alpha disk and saw that instabilities occur. And these instabilities are due to density and thermal instabilities. And they cause a runaway temperature in the iron corona, to where the temperatures are raised. The proton temperature is raised to like 10 to the 12 Kelvin. And the electron's temperature also is raised that high, but then the electrons have a more effective mechanism in cooling. And I'm not gonna go through this, but this right here was the reason why we suspected that it was a supermassive black hole, because of the Eddington luminosity, which showed that the mass luminosity relationship, that we have a large mass from the luminosity. And then the causality relationship, which showed that this object, the variability showed that this object is small. And then also, we know that energy should be released. And this is just due to accretion. So for a non-rotating black hole, you only get like 5.7% of the mass energy. And then for a rotating black hole, a maximum rotating black hole, you can get up to 42%. And so this is not even including the Penrose process or even the Blanchard-Denied model. So my method is that I did Monte Carlo computer simulations of 2,000 to 70,000 scattering events. And the reason why I didn't do any more is because you'll see that it only, when you look at with the particles that come out, each individual particle, you do a whole lot of particles, it just fills up the area. So I had to, stop there. I wanted to stop there because then I wanted to be able to distinguish the different particles. The infalling photons had a monochromatic distribution or black body distribution or a power law distribution of the infalling photons. So I looked at all of those. The ingredients, I used general relativity, the Kerr metric to define the particle orbits and the escape conditions. I used the conserved energy and angular momentum parameter. That's that conserved energy, and then the azimuthal parameter. And these are conserved parameters that are measured by an observer at infinity. And that's us. I use transformations from the Boyer-Lincoln coordinate frame, okay, and that's us, the observer at infinity, to the local non-rotating frame. Now, the Boyer-Lincoln coordinate frame, like I said, is for the observer at infinity. The local non-rotating frame is the local Minkowski frame, and that's for flat space-time, and in that frame is where I perform the scattering processes. So the next, so this leads us to special relativity. I use special relativity in the local non-rotating frame. So again, like the local non-rotating frame is the local frame, and where you do the physical processes. So that was the scattering processes were done there. Lorentz transformations between inertia frames were performed, and Lorentz invariant laws were applied. Next, which was very important, I used the cross sections. Now, I used the cross section in application of the Monte Carlo method, wherein I pick, in order to pick the angles, I use a Monte Carlo random sampling. And I did it in the electrons rest frame for Penrose Compton scattering. And in the, I'm not gonna even mention the gamma P, but I used the, in order to perform the gamma pair production, I did it in the center of momentum frame. And from these angles, I was able to calculate final energies. So the outcome was that I was able to extract energy and momentum, and in the form of the 4-momentum vector. So I was able to get the energy and the 3 space components. So in other words, not only was I able to get energy, now I'm able to describe the structure of the jets from the momenta components. This is a very busy diagram, but I have to say this because I went through the, well, I'm not going to say it was trouble, but for a long time after I had decided to work on the Penrose mechanism, I first investigated the different accretion disk models so that I could make sure that my particles that I used for scattering events were consistent with theory. So the geometrical and dynamical structure of accretion disk depends on this small m dot, which is the ratio of the accretion rate to the Eddington accretion rate. And we know that the Eddington accretion rate is the maximum accretion that you can have before the object blows itself apart from radiation pressure. And then this epsilon, which is L over the accretion rate times C, is the radiation efficiency. And that is how effective is binding energy radiated away. The thin disk that I talked about, the alpha disk, it radiates in the UV and soft X-ray. And the energy of that disk is up to, of the thin disk is up to 3.5 keV. What Lightman found was that the thin disk was unstable. And so he, in his original paper, he was saying that rings would form, these optically thick rings surrounded by optically thin regions. And then due to the instability, then he only had speculated that perhaps it was that the disk would just, get one region gets hotter and one gets colder, and then eventually the instabilities would just destroy it, and a cycle would start. Or so that was one way. But like I said, he was only speculating. And then as further investigations occurred, then we saw that the two temperature bistable disk could occur, and Narayan, I hope I'm pronouncing that right. I remember listening to his talk, and he was talking about the iron corona accretion. And then the question that I asked him was, could it oscillate between thin disk and iron corona phase and in Israel? And he told me yes. So I was really happy about that. Now, the two temperature bistable disk, recall that I said that the electron temperature is around 10 to the 9 Kelvin and the proton 10 to the 12 Kelvin. Now, when the temperature is that high for the proton, then you can have proton scatterings in which a neutral pion is emitted, and then this neutral pion could decay into gamma rays, and the gamma rays could pair produce. And so the result is that the energy of the gamma ray peaks around about 75 MeV, and the electron-positron pair around 35 MeV. Now, Jean Eilick, she had looked at this, and then Narayan, he looked at it in 1997 for a power law distribution, and she had looked at it for a Maxwell-Boltzmann distribution. So the important things that we learned from the disk investigations is that the disk can undergo instability cycles. The corona, or the advection-dominated accretion flow, is a poor radiator. In the advection-dominated accretion flow, also with that small m dot, much less than 1, the material is stored and advected into the black hole. And also we found that funnels could form, and that was predicted, I think, by Martin Rees. Okay, now this is from my disk, my accretion disk calculation. I performed a computer simulation, and I included Norbert Scott and Thorne's disk, relativistic disk. I included Eilick's equations from the iron corona, and she had looked at it from a relativistic point of view. And then I used the conditions, when the thin disk would become an iron corona, two temperature disk. And so I know that these things are small, but anyway, I was able to put in alpha and put in different parameters, and I was able to get temperatures out for the thermal temperature, the electrons temperature, the ions temperature. And then I was able to see what the mass accretion rate would have to be in order for the iron corona to form. And so these are the energies. The temperatures that I got out are the equivalent I used to define my energies that I use in the scattering processes. So the overall result is that I got the energy and the three space components, the radial component, the theta component, and the phi azimuthal component of the momentum. So from Penrose company got scattering, now this is just the overview. For input energy range from 5 eV to 1 MeV. So these were photons falling inward. I was able to, extract energy of the order of 15 keV up to 14 MeV. For Penrose pair production, gamma-gamma pair production, for the input energy range of 3.5 keV to 50 keV, I was able to get energy out back, or particles escaping with energies of the order of 2 MeV to 10 MeV. And that was for the thin disk. And then for the iron corona, after the disk, due to the instabilities, I was able to get energies ranging from 2 MeV up to 54 GeV. I probably could have gotten higher, but my program crashed. And usually when that happened, it was like I was trying to do something that was impossible. But I'm sure that you could get higher energies out, but you have to know how to have a way to populate the orbits. And this way I was populating the orbits with under the conditions of the accretion disk that I had investigated. And also I found that particles escape in the form of vortical polar jets. And that's these jets that are orbiting concentric to the polar axis. And the particles are escaping in these coil-like distributions. So now 1, 2, and 3 are all consistent with observations. And over here, I just had a little diagram of the processes that I already talked about. So the Penrose-Williams mechanism. Now, the reason why I called it the Penrose-Williams mechanism is because people were investigating the Blanchard-denied Penrose process. And so I wanted to make sure that it was, there was a distinction between the two. So it's a 4-dimensional general relativity mathematical model, and I use space-time frame dragging. This model appears to overcome problems that were associated with the Blanchard-denied type model. And I just want to mention that when I initially started working on this, my goal was to explain the energy source of quasars. So I started off with the Blanchard-denied type model. I worked on it for a while, and I was doing the analytic part of it. And so my advisor, that this is in graduate school, he taught electrodynamics. And so we got to a point to where I was trying to create the particles in the field, or the way that Blanchard and Denied had said to create them, by having a photon cross the field, cross the line of the magnetic field, and it would result in a electron-positron pair cascade. But we found that it was impossible to do that with the strength of the magnetic field that theoretical calculations proposed, and that was about 10 to the 4th Gauss. The magnetic field, in order to start this Penrose pair production cascade, would have to be comparable to the magnetic field of a neutron star. So that's why I stopped working on the Blanchard-denied type model. The model that I'm working on is self-consistent, and it constitutes a complete theory to extract energy, as I explained. Now, this is the diagram that I drew. So here, the iron corona, the accretion disk. So the particles, they escape, and when they escape, this is due to the frame dragging. And the result of the frame dragging it creates a gravitomagnetic field, and I'll talk about that, the significance of that later. But the particles, they escape along these vortical orbits. And what's unique about this is that these particles are escaping along these vortical orbits. They are charged particles as well as photons. And when I talk about the gravitomagnetic field, the gravitomagnetic field, it's the gravitational analog of a magnetic field. And so it acts on all particles. It acts on the momentum of a particle. So it acts on gamma ray photons as well as electron-positron pairs. And so from electrodynamics, if the particles are escaping in these coil-like, and the escape angles here is just overemphasized, but they're like, very, very small. And so it's like a coil, and I'll talk more about this. So if the particles are escaping along these vortical orbits, then they will be associated with the magnetic field, and the magnetic field would be sort of like a solenoid magnetic field. And I want to, my future plan is to do a evolution of it and confirm what I'm saying. So in order to calculate the outgoing luminosity, first of all, when I acquired the four momenta of the particles, I acquired four momenta for each particle. And so I have to find out a way how to get a luminosity from these particles. And so this is what I did. So this is the luminosity of the escaping particles, and it's the normal luminosity for pi times the distance squared times the flux of the escaping particles. So I had to first apply the escape conditions, because not all the particles escape. And so again, this is the flux of the escaping particles. When you break this down, so the flux is h nu times the number of the emittance of photons that are escaping. The emittance of photons escaping is proportional to these fitting factors, and I'll talk more. I'm going to talk about those, times the number of the emittance of photons falling in or as incident particles, minus those that are captured. Okay, so this emittance of photons. Okay, so these are the emittance of photons in. Okay, so here is the power law distribution of the accretion disk photons. This is what in the emittance in is equal to. K and alpha are the photon spectral index. I'm sorry, K and alpha, the photon spectral index, is determined from observations. This in capture, this is the number of the photons that are captured. These F sub n's, they are defined, they define the fraction of the particles that undergo scattering events, because not all the particles would undergo scattering events. This would depend on these parameters, and in the next slide I explain what these fitting parameters are. Importantly, I use the conservation of photon number in the Compton scattering processes. So I use it also in the pair production process too. And then the emittance of the particles in was normalized to the number of incident photons from the disk. So I explain that a little bit more. So these fitting factors, they are the fraction of the particles that undergo scattering events. It's like a probability. And it varies from greater than or equal to 0 to less than or equal to 1. The Fn, which you have Fn, Fn, the n is equal to 1 and 2 for the Penrose Compton scattering. So alpha 1 is the fraction of the disk photons intersecting the scattering radius, which I call R sub S, coming from the inner region of the accretion disk of height h. And this is what my F1, I derived it to be. F2 is the fraction scattered, and this is dependent on the total cross-section, which is the effective area of the target particle. The Klein-Nishina is the proportional to 1 over gamma of E, and then a pair production, it's 1 over the energy of the the target particle, which is gamma 2, and then the incident particle. So F2, I define it to be the number of scattered photons divided by the total number of infalling disk photons. F3, then this is for pair production. It's the fraction of the infalling disk photons intersecting the scattering radius. And this is for what I call secondary Penrose Compton scattering, because the electrons that are produced in the Penrose pair production, they're not, you can't get a luminosity directly from them. So once the pairs were produced, I had them undergo Penrose Compton scattering to get a luminosity. So that's why I called the secondary Penrose Compton scattering. F4 is the fraction of the infalling disk undergoing the secondary Penrose Compton scattering, and that's dependent on the cross section. So that's equal to F2, F2. And then F5 is the fraction of the electron-positron pairs undergoing the secondary Penrose Compton scattering, and that's dependent on the expansion rate of the jet. So all of these were parameters, factors that I had to put in order to fit the model luminosity to what we observe. And I'll show you what I'm talking about. Okay, I put okay, I calculated, I duplicated the spectra of quasar 3C279 and 3C273. On the following diagrams, you may not be able to see it because it's so small. So I just used one. I just brought this one so that you can see where the Penrose Compton scattering particles are emitted, and that's in this regime. Okay, so that's like what's that, about 4 kb, something like that. And then the Penrose pair production, the particles are produced in this regime. So this is the diagram of these are observations for 3C279. And I just kind of labeled from the accretion disk models where the outer and the middle disk accretion would be emitted in this region. This would be the inner accretion disk, and this is instability. These particles are, so you have particles emitted in this regime here, and Ehrlich particles, the ones that I said would have energies of the order of 75 MeV and what is 45 MeV. So this is where her particles would be, and then you have emission in this regime. This would be particles that are emitted by synchrotron radiation. So I knew you couldn't hardly see this, but this is the same diagram that I showed you. And then this is 3C273. These are my model spectrum. So here I calculated actually where the accretion disk would be. This is from Penrose Compton scattering by equatorially confined target electrons. This is by non-equatorial, Penrose Compton scattering by non-equatorial confined electrons. Well, they're just non-equatorially confined. Let me say that. Did I say that right? Right. Okay, let me say it another way. So these target particles have orbits that orbit outside the equatorial plane. And this spectra is from the luminosity from the Penrose pair production electrons. So you see, like, this is if every particle scatters, okay? So this is 3C279. Then you get a similar spectra for 3C273. This is from Penrose complex scattering by target particles confined to the equatorial plane. Again, this is for non-equatorial confined targets. And then this is from the pair production. So if you take those fitting factors, because we know that every particle is not going to scatter, you could actually fit it to look to the observed luminosity. So you see the Penrose mechanism, it emits radiation in these three separate regimes, which are consistent with what we observe. And these numbers, there I'll explain them. These numbers are from the continuum spectrum, because each one of these numbers represent a monochromatic distribution of infalling photons. And so when when the numbers are just let me go on. So the numbers are represented. The numbers represent the peak distribution of the escaping particles. So that's like the continuum. So here that's just the distribution of the particles, of the escaping particles. So let me, okay. This is just a diagram of the galactic black hole. Yeah. This is what we observe for the galactic black hole. This is from the model calculation. So here, this is the accretion disk. I took a monochromatic particle from here, and this is the distribution that it gave me. So this is from Penrose complex scattering by equatorial targets, and this is from gamma pair production. So notice that this is for a thin disk accretion. Notice that the non-equatorial target distribution isn't here. So that's why I suspect that the galactic black hole does not undergo that instability that we observe in quasars. Just to show you, okay, so this is the these are the radial components, and each one of these little dots is a particle, escaping particle. That's the radial component. That's the polar components. This is the azimuthal components, and notice that the azimuthal components are linear to the energy. So the higher the energy, the larger the azimuthal component. Okay, now I want to get to this. This is the a plot of the scattering escaping angles in the polar direction. So if we just looked at this in 2 dimensions, it just looked like the radiation is just is toward the equatorial plane. But then when you look at it in 3 dimensions, these are actually the escaping angles, which is like the pitch angle of the coil. Okay, this is from gamma pair production. And so this is that's the radial component. This is the azimuthal component. I'm going through these sides. This is the actually that was the polar component. This is the azimuthal component. Again, these are the escaping angles. The escaping angles for the electron-positron pairs is the escaping angles are only 0.5 degrees above the equatorial plane. So you have this strong coil-like distribution. Now, I know right over time, but the gravitomagnetic field is responsible for these vertical orbits. The gravitomagnetic field is the gravitational analog of a magnetic field. it's really like a general relativistic Coriolis-like force, and it acts on the momentum of the particles. I wanted to look at this polar coordinate because in some of my papers, I had mentioned that you can get asymmetrical distribution. It turns out that the curved black hole can't do that. But if the metric were derived so that reflection symmetry above and below the equatorial plane was not assumed, then you could actually get asymmetrical distributions, because this part would give you symmetrical distributions, which is this angle, this diagram. And this part would cause asymmetrical distributions. But this tensor component is 0 for the curve metric, because it was assumed that this component in the metric was equal to 0. Okay, so that's just the vortical orbits, and these are the escaping orbits. And I talked about for the photons that are escaping from Penrose Compton scattering, you get a larger escaping angle. Okay. So here we have observed, we know that something is being being emitted in a coil distribution. It could be particles, or it could be magnetic fields from the rotation measure, or it could be both. This is a diagram that someone drew indicating the Blanchard-Denard magnetic field. Yeah, I was going to talk about Blanchard-Denard, but I won't. So I'm just going to say that when I talked about the Penrose, the Blanchard-Denard Penrose process, well, it was shown that that process doesn't work. So the conclusion is that there's strong evidence that black holes exist in nature. Black holes that exist in nature appear to be rotating. They are indeed fascinating objects in the universe. And it appears that the energy momentum is extracted from my analysis of the Penrose mechanism, and perhaps assisted by the Blanchard-Denard plane type model away from the black hole that's far away from the accretion disk. Thank you.
Thank you very much, Reva, for a very deep talk on a very deep subject. So there is time for some questions. Please just raise your hand. So yeah, I'll wait for questions. Let me ask the first question, Reva. Actually, it is the part that you rushed through at the end, because I was listening to your talk and I was thinking, many of us keep thinking about and working with Blanford's Nyack. And you have a completely different way of doing things. You're looking at particle pair production, Compton scattering, and all that. So the thought that came to me was, can we have both in a given object? Is it possible that what we observe is really combination of Penrose, Blanford's Nyack, and Penrose Williams? Except you had a slide which says Blanford's Nyack doesn't work. So I don't know, maybe you want to explain in a couple of minutes what that is about?
Okay. Well, what the Blanchard-Denard Penrose process doesn't work, where they were assuming that the magnetic field lines inside the ergosphere would hinder the particles and send them on retrograde orbits or negative energy orbits. So that doesn't work. But the Blanchard-Denard type model, what I initially wanted to do was to extract the particle energies and then use the Blanchard-Denard type model to accelerate them. Now, they could occur at the same time, because the problems with the Blanchard-Denard model is that it radiates, well, it doesn't radiate, but the energy that's extracted is electromagnetic energy and not particle energies. And so where the Blanchard-Denard model operates, that's where the funnel is. And so you need particles that are not part of the accretion disk, which are the Penrose process particles. And then also in my paper 2004, it showed that a lot of these particles, many of them have turning points and they do not even interact with the accretion disk. Now, some of them do, but the electron-positron pairs, they escape, almost void of the accretion disk. So the Blanford model and the Penrose-Williams model, they could operate together.
Okay. Very nice. Yeah, thank you. I would like to see how the two can be combined.
Yes.
Right. Okay, so do we have any other questions? Any raised hands?
Yeah. Justina Yang.
Yeah,
Why
thank
am
you
I
for the
not
talk.
seeing it? Please go ahead. Yeah.
Okay, thanks. I had a question about the Monte Carlo simulations that you did. What was the spatial distribution of the infalling photons?
Okay, I assume like the scattering processes, they took place in the ergosphere. So to get the maximum amount of energy, I let the particles fall radially inward along the equatorial plane. So that's where the scattering process took place in the equatorial plane. The non-equatorial targets, the target particles, they're particles that are on these spherical-like orbits, and the orbits, they oscillate between a high a latitude, above the plane, and then they circle around. And Wilkes, he wrote a paper about this, I think it's 1972, and they reach a maximum latitude where the polar coordinate momentum goes to 0. Okay, and then they start their trajectories back. They pass through the equatorial plane and they go to a certain latitude. That latitude for the electrons targets was like 29 degrees. That was the maximum. So so the particles are constantly are constantly oscillating between a maximum latitude, and then it goes below the plane. So those were for the non-equatorial targets, and they call those spherical-like orbits.
Okay, do we have any other questions? If not, before we close the session, let's thank Reva once again. Thank you very much, Reva. Thank you for coming and sharing your work with us. So we will close the session at this point.
Okay, thank you all.